When you want, I can start.
Yes, please.
Okay. Good evening to everybody. I am Pierandrea Vergallo from University of Salento. The title of my talk is Hydrodynamic Type System and Homogeneous Hamiltonian Operators, a Necessary Condition of Compatibility. It is a work based on a work with joint with Raffaele Vitolo. And so we can start. At first, I need to underline and to recall for all of you notion that surely you know, that is what is an Hamiltonian operator, but I know they are useful for notations. We are dealing with the evolutionary system of PDEs of such a form here. And in particular, we say that such an evolutionary system admits an Hamiltonian formulation in such a form here, where A is a matrix differential operator, like this, such that the associated bracket, that is this one, is a Poisson bracket. In particular, the notation is based on this notation here, where the sigma indicates the number of sigma times the x derivatives in this way here. Now, let us recall what is an homogeneous Hamiltonian operator. An homogeneous Hamiltonian operator of order n in dimension 1 has this form here, where bijk and so on, all the coefficient depends on the dependent variable. Here, the concept of homogeneity is described by these two rules that are natural rules on grading of the operator. The important fact is that these operators are form invariant under transformation, point transformation of the dependent variable in such a way that is described in form. Let us consider at first one kind of homogeneous Hamiltonian operators that are first order homogeneous Hamiltonian operator. First order homogeneous Hamiltonian operator is that is described in this way here, and we choose Gij to be non-degenerate. Dubrovin and Novikov in 1983 presented the conditions of Hamiltonianity of this operator here. And if we consider the inverse metric of Gij, we say that these symbols described by this relation here are exactly the Christoffel symbols of the metric Gij, and the metric has to be flat. Moreover, we consider hydrodynamic type system that in this case are quasi-linear, are called quasi-linear systems of first order, that are also called in such a way hydrodynamic type system. The important fact here is that these systems are invariant also with under these kind of transformations. Now, an important result was presented by Tsaryov, and it represents a way to connect first order homogeneous Hamiltonian operator and hydrodynamic type systems. In particular, he proved that an hydrodynamic type system admits an Hamiltonian formulation in such a way 8 through a first order homogeneous Hamiltonian operator if and only if these two sets of conditions are satisfied by the operator and the system. The important fact is that in the proof, it is used explicitly an Hamiltonian function h, which in general can be difficult to find. Let us see an example. Here we have the WDVV equation that is known in this way here, but we can use a change of variable a, b, c in such a way that the equation becomes a system. Then a system, given the system, we can consider this first metric here and construct the associated homogeneous Hamiltonian operator that has this form here, as we've seen before. Then the system, given the Hamiltonian, that is this one, can be written by using Hamiltonian formalism, that is an Hamiltonian system. The important fact, obviously, is that the two sets of conditions described here by Tsaryov theorem are satisfied by this operator described by the metric and by the system here, as we expect. What we would like to do is to introduce and to produce generalizations of this result. In particular, we'd like to do to present a compatibility condition between second-order homogeneous Hamiltonian operator, and this is totally new, and it was presented by me, by Raffaele Vitolo and me in our last article. And for third-order homogeneous Hamiltonian operator, this work was just done by Genia Ferapontov, Maxim Pavlov, and Raffaele Vitolo. Moreover, we can apply this method in general for higher orders homogeneous Hamiltonian operator and to see some results about non-local operators. At first, we recall what is a symmetry in a conservation law, but in particular, you obviously know it. And I recall these notions for people who are not so practical with this. In particular, we say that symmetries are vector functions which satisfies this system here, well, LF is the linearization associated to the system F, but it is a Frechet derivative of F. Moreover, if we have a conservation law omega, we can associate a cosymmetry phi such that it satisfies this symmetry here. Now we have the formal adjoint of the linearization LF, which is L star F. Now, Kersten, Krasicic, and Verbowetsky in 2003 presented a way to work with the symmetries and cosymmetries in the theory of coverings. In particular, we'd like to underline the cotangent covering. That is the space in which the new variable p, which are in the same number as the dependent variable u, satisfy these conditions here. And in particular, if we consider a Hamiltonian operator, we have the cotangent covering here and this condition. We'll see it later. The important fact is that we can associate a given operator of such a form, a linear function in such a form here, where p, j, sigma are the new variables we present. This is not so unusual because it is a quite common way to deal with operators in algebraic geometry. What is the necessary condition that we mentioned in our title? In particular, we know that Hamiltonian equation shows a correspondence between conservation laws and symmetries. In particular, if A is an Hamiltonian operator for an evolutionary system, this equation here is satisfied. Vice versa, if we have an operator which satisfies this equation here, we say that it is a bivector. So what we have is that if we have an operator, an Hamiltonian operator, it has to satisfy this condition here. And now we can consider this as a necessary condition for an operator to be Hamiltonian. In particular, for a given
operation. I'm sorry, just one question. What means cotangent covering, or you will speak about it?
Yeah,
you introduced conception cotangent covering. I don't understand.
Cotangent covering is this one, and it was presented by Kersten, Krasicic, and Verbowetsky. In our case, we can consider it as a space where the new set of variable p, which are the same number of the dependent variable, satisfy this equation here, which is the adjoint of.
Sorry, I don't understand what means cotangent covering, or maybe it's very simple. I don't. What it means cotangent covering? What it means? What means?
We can consider this space as a geometric space, and it represents a covering of a given equation F. Okay. By the extension of this satisfied equation here.
Thank you.
Okay. So on the cotangent covering, that is that one that we said we've just seen, the operator has A must satisfy the equation here, that is this equation here. So if we have a cotangent covering, we have that this adjoint of the linearization must be 0, And so this part is 0, and so this part has to be equal to 0. This condition is really important because it is invariant. We recall that hydrodynamic type system are invariant under transformation of U. Homogeneous Hamiltonian operator are invariant under transformation of U, and also these are considered are invariant. These spaces are invariant. Let us see an example. Let us start from the KdV equation, which is very famous, and perhaps lots of you knows this example. This is the equation, and we can compute the linearization of the equation here. Then we can compute the adjoint of the linearization and associate the cotangent covering for the KdV equation. Here we have the number, the P variable, which satisfies this equation here. Then an Hamiltonian operator has to satisfy this condition here, and we have here two solutions of this equation. In particular, it is easy to consider, for example, the first one, to put it here, and then to compute that this one is equal to 0. Sorry, okay. Now let us recall first order homogeneous operator, because we need to associate to this operator a linear vector function that is this one. If we associate this linear vector function, we can compute our necessary condition, and we obtained this theorem here. If we have a first order homogeneous Hamiltonian operator and another dynamic type system as in 17, the compatibility condition, that is this one, on the cotangent covering are exactly these two. The important fact is that these two conditions are exactly the same presented in the theorem by Tsaryov. The important fact here is that for this theorem, the proof does not involve the use of an explicit Hamiltonian H. Now we would like to generalize this way to work for higher order homogeneous Hamiltonian operators, in particular for second order here. A second order homogeneous Hamiltonian operator is an operator that can be written in such a way where Gij is chosen to be non-degenerate, and it is skew symmetric. If we consider the inverse metric of Gij, we say that given these symbols here defined as described here, they transform as Christoffel symbols of a linear connection, and this connection must be flat and symmetric. So if we have a connection, we can consider flat connections, flat coordinates for the given connection, and the operator can be written in an easier way, that is this one, described in 19. If we consider again the inverse metric, this metric has to satisfy this form here, has this form. In particular, Tijk is a free form, and G0ij is a true form. They are constant, and in particular, they are skew symmetric. Let us see two examples of these kind of tensors, this kind of metrics. The first one is for n equal to 2, and it is in this. It can be written. It is written in this simple way. Whereas for n equal to 4, we have this more complicated but easy to compute way. These are the most general examples for n equal to 4 and 2. Why don't we study n equal for odd numbers? Is that in this case, we know that the associated matrix is degenerate. Whenever we have skew symmetric and odd dimensional matrices, we have degeneration, and we don't want it. So let us recall again second order homogeneous Hamiltonian operator, but now we consider potential coordinates in such a way here. Now, the equation becomes easier to write, and we can write it in such a way, and the operator is even easier. The fact is that now the operator becomes of order 0. Now we have this simple operator, and as we did before, we can associate a linear vector function that is this simple equation here. Now we know the necessary condition and how to compute them, and we proved with Raffaele Vitolo this theorem here. The compatibility condition for the operator, this one, to be compatible with this equation here, system here, for an Hamiltonian operator, is to satisfy these sets of conditions. The important thing that we proved is that the system is in involution, and also in this theorem, we do not need the use of an Hamiltonian or an explicit Hamiltonian function. Let us see an example for n equal to 4. In particular, we take this general matrix here, and then we choose some coefficient. We fix some coefficients. Here is the setting. And then we can see that solving these sets of equation here for the given metric, we obtain a family of system of 10 parameters. This is the family of system that was the solution of our system. The important fact is that this is rational. Now, moreover, we studied this system in the general case for a generic metric of this kind here. And we found that if it is non-degenerate, we can solve it explicitly for the unknown function Vy, and the solution depends by at most 23 parameters. In particular, the resulting systems are linearly degenerate and diagonalizable. In particular, if you have these two conditions, 7a proved that the system is semi-Hamiltonian. Moreover, we found that the eigenvalues of the matrix of velocities are real and with algebraic multiplicity equal to 2. Another important fact about the second order homogeneous Hamiltonian operator is their projective invariance. Let us consider a projective transformation in such a way here. We have a transformation from Pn to Pn, and we consider the transformation of the dependent variable in such a way, where delta is a fixed affine equation function of this kind here. These are constants and are fixed. In particular, we proved that for second order homogeneous Hamiltonian operator, the metric Gij, in particular is inverse, is transformed by these sorts of transformations in this way here. We underline the fact that we have this quantity here elevated by 3 in our example. And the other important fact is that the numerator of this quantity is exactly of the same type of the given G, of the starting G. That is this type here. Okay, moreover, we can choose reciprocal transformations of this kind here, where delta is the same as the same type as described in the previous slide, that is this type here. And we proved with Raffaele Vitolo that projective reciprocal transformations brings canonical second order homogeneous Hamiltonian operator into operator of the same form. In such a sense, they are form invariant under these transformations. This is not so uncommon, this is not so unusual, because we can consider third order homogeneous Hamiltonian operator and see that lots of things seems to be similar. In particular, we have that homogeneous Hamiltonian operator of third order can be written in such a way here with Potiomin canonical form. They can be simplified in this way, and moreover, they can be written in by using the way described before, with the help of these sets of variables. In particular, this is the associative vector function of the operator. Again, we can compute the necessary condition. These conditions were computed by Ferapontov, Pavlov, and Vitolo in 2017, and they says that if we have a homogeneous Hamiltonian operator of a third order and another dynamic type system here of this kind, it admits an Hamiltonian formulation with the operator if and only if these three sets of conditions are satisfied. In such a sense, they are similar to this one. Okay, the important fact here is that the system is in involution also for third order homogeneous Hamiltonian operator, and the solution is reduced to linear algebra problem with the unknown Gij and Vui. In our case, it is the same in second order homogeneous Hamiltonian operator. It is the same for unknown Gij, but we think it could be the same also for the unknown Vuij. Also, in this case, we do not need an Hamiltonian, an explicit Hamiltonian function H. Ferapontov, Pavlov, and Vitolo proved something that is quite similar to what we found in second order operators. That is, if we consider projective transformations on the metric, the given metric G, it transforms in such a way here, where delta is the delta seen before. I underline the fact that 34 is quite similar to 30. Here we have 3 for second order homogeneous Hamiltonian operator, and here we have 4. Moreover, they proved that Gij is a Monge metric for in Pn. As similarly to what we did in second order homogeneous Hamiltonian operators, was found for third order. In particular, they transform under projective reciprocal transformations. If I take a third order homogeneous Hamiltonian operator and then I transform it by projective reciprocal transformations, it becomes an object, an operator of the same type, of the same form. So what can we conjecture? The first conjecture is that if we consider the leading term Gij of a given n-order homogeneous Hamiltonian operator, I recall that the form of the operator is exactly this one. So the leading term here, associated to the coefficient of the higher derivative, now we can conjecture that applying projective transformations, the metrics transform as follows, with delta elevated by n+1. We knew that it was verified for third order homogeneous Hamiltonian operator and for second order homogeneous Hamiltonian operator. Moreover, we can say that if we consider reciprocal and projective transformations, they bring homogeneous Hamiltonian operator of n order, of order n, into operator of the same type, of order n, in the same form. In particular, all these results that we obtain with Raffaele and the results previously obtained by Ferapontov, Pavlov, and Vitolo can be generalized for every order. It is quite, it is our conjecture, it is not done, but we think that it could be possible. Now, what we would like to do is to analyze another type of operators, which are non-local operators. We start from this formula here, and we can compute explicitly this formula here. In our case, is if phi is a symmetry. Then we have these conditions here, and we consider this quantity, we put this quantity equal to Rx, and this quantity equal to RT. So we introduce a new variable that is R, and it is called a non-local variable. This work was done by Kersten, Krasilcic, and Verbowiecki. So if we consider first-order homogeneous Hamiltonian operators, that are operators that can be written in this form here, there is the non-locality, we recall that it is an Hamiltonian operator, and it has these properties here. The first part, that is this part here, is just a local first-order homogeneous Hamiltonian operator. Moreover, phi, this is a symmetry for the system. The curvature tensor has to satisfy this condition here, and we have two more conditions here. The expression of B can be translated by using the new variables, and it becomes the first type, as we've seen before, plus this type here with the non-local variable R. Given this operator, we can compute again the conditions, and we can see that if we have an operator non-local, such a way B, that is this one, whose non-local part is defined by a symmetry, as we did before, this is capital W. For a given hydrodynamic type system, the compatibility conditions are exactly the same as described in Saryov theorem, but also as described in what we found using these, we can say, alternative method. Also, in this way, we do not need to give an explicit Hamiltonian function. Now, what are the future perspectives of our work? In particular, we can use this method to study the compatibility conditions for new types of operator. In particular, we can consider non-local Dubrovin-Novikov operator and to try to understand which are the conditions for a system that can be written in this way here, where Wi depends only on the dependent variable, the dependent variables ui and the independent variable x. This is a work in progress. Another work in progress is to study, on the way of our leading conjectures, the projective geometry that can be associated to second-order homogeneous Hamiltonian operator. This is still in work in progress with Raffaele Vitolo. Moreover, we can study compatibility conditions for systems of a given type that can be hydrodynamic type systems or different type of system, but to find conditions for other operators which are symplectic operators. And moreover, it could be possible to study something more about second-order homogeneous Hamiltonian operator with a non-local term. So this is the end of my talk, and I thank you very much for the attention.
Okay, thank you very much.
Thank you.
Well, quite simple and very nice. Any questions, remarks? Raffaele, don't you want to add something?
Well, I can add the fact that what we found is basically that besides third-order operators, for which we already found nice projective geometric invariance properties, also second-order operators seem to have similar features. We still do not understand what is the geometric nature of the projective geometric object which underlies the second-order.
Yeah, I just wanted to
operator. This is still to be understood. We are trying to understand what kind of objects they are. Pier Andrea spoke about the Monge matrix. Indeed, third order operators correspond to a certain type of projective variety. It's called quadratic line complex. There are special types of quadratic line complexes. A quadratic line complex is
Excuse me,
basically,
and they are somehow related to linearly degenerate equations, yes?
yes. But the point is that third order operators are related to non-diagonalizable linearly degenerate systems. Why? Second order operators are related to what seems to be, at least in the case n equals 4, diagonalizable linearly degenerate system. And yes, thanks, Pier Andrea.
The result.
Yes, so something that Pier Andrea didn't say is that when a system is semi-Hamiltonian and has distinct eigenvalues, the theorem by Sergei-Tsaryov applies and the system results integrable. But the point is that such systems, all the systems which are associated to second order homogeneous operators are diagonalizable with two eigenvalues of algebraic multiplicity 2. So they are not all distinct, they collapse. And the point is that it's not 100% sure that Tsaryov theorem can be applied in this case. It's likely yes, but and recent results by Maxime Pavlov, Zhenya Ferapontov, and others show that it is possible to integrate such systems, but there is no general statement in this sense. And we need to do a deeper investigation to understand if they are integrable. At the moment, I would say that it's highly likely that they are integrable. Not 100% sure.
What do you mean by integrable?
Integrable by the method of generalized autograph transform.
I see.
Basically, they're linearizable, basically. Using higher symmetries of hydrodynamic type.
Thank you. More questions, more remarks? No question? No remark? Okay, then I would like to say goodbye and invite you to the next seminar, which will take place exactly in a week. Nice to see you here. Bye-bye.
Bye-bye to everybody.
Bye, thank you.
Thank you. Goodbye.